we're going to talk about how to detect whether a hypergraph is acyclic. Okay. All right. I hope you still remember what we talked about last time. Okay. So if there's only one thing I want you to remember for today, it will be the definition of acyclic hypergraphs. Okay. Um, Not every one of you here was here last week. Okay, so I'm going to very quickly review the definition. Okay, um, first of all, hypergraph, hypergraph. Okay, um, and how does this differ from our traditional understanding of graphs? Okay, so as you can see, a pair V and E. V stands for a set of vertices, and E stands for a set of edges. Okay, so far so good, right? Now the only thing is um, the definition of edge changes. Okay, so before, traditionally, every time we thought about a graph, we would be saying every edge should contain just two vertices. Okay, so you drop this requirement. Okay, so an edge, which is called a hyper edge. Now, hyper, when we go hyper, we're high. See what I'm saying? Okay, so hyper edge. So a hyper edge, which generalizes the traditional notion of edge, right? A hyper edge says it's okay how many vertices you put into this uh, hyper edge, right? It can be two, can also be one. Okay, that's quite interesting. All right, just one vertex in this hyper edge. It can also be zero, so that would refer to an empty edge, and it can be three, four, etc., etc. Right. So as long as it's a subset of V, then that will be fine. Good. And the next notion is acyclicity. Okay, acyclicity. What's happening? Where is it? Okay. Oops. Okay. It doesn't write. And why is that? I don't know. So I guess okay. Um, so a cyclic graph. Okay. Now this is a little bit unusual in the following sense. I can tell you because now you have hyper edges rather than edges. What it means by a cycle becomes ambiguous. Okay, ambiguous. I can tell you in the literature there are multiple ways to formulate the concept of cycle, and therefore the concept of acyclicity. Okay, so the version that we talk about here is a powerful version that generalizes a lot of many other definitions. Okay, and I find it quite natural to define it through a tree. Okay, there are other ways to define it, and uh, some of them are quite complex. One thing I'd like to point out is, unlike traditional graphs, here we're not going to talk about cycles first and then say, okay, this is a graph without cycles. And why? Because it will be very ambiguous, actually very confusing sometimes, and sometimes even contentious. Okay, so I could be inviting comments from students like, hey, you see, that's a cycle in my opinion. How come you don't count it? Okay, so what am I going to say? All right. So I decide not to go down that direction. Okay. So last time we defined acyclicity in the following way. Okay, so if I could find a tree for your graph, and then uh, your graph is acyclic. Okay, but this tree has a lot of stringent requirements. Okay, so G is acyclic if there exists a tree, this T. Okay, and this T will have to satisfy two requirements. Okay, so the first requirement is so-called 1-1 requirement. So this basically says every node in the tree corresponds to in a hyperedge in the graph. Okay, so I'm not gonna write down the words for the definition because that takes time. However, I'm going to demonstrate this using an example that I prepared in my lecture notes. Okay, so here um, I'm showing you a graph with vertices A, B to H. Okay, and what you are seeing here are the hyperedges for the graph. Okay, get used to this. Okay, um, so hyperedges for the graph. Okay, so for example, we can have H. That's a hyperedge. All right, and this is a tree T. Okay, so as you can see here, every node of the tree corresponds to a hypergraph. Okay, so I understand, trees, graphs, they could be confusing, but I want you to think about discrete mathematics definition, right? So I got a tree here. To define a tree, I just have to define its vertex. You see what I'm saying? Okay, I'll refrain from using the word vertex because vertex you could understand them as you could understand it as a vertex in the hypergraph, right? So I'll be very careful. I'll be using the notion node. That's basically synonym for vertex. When I refer to something, when I refer to a vertex in a tree, so as long as I can tell you what are the nodes and what are the edges inside the tree, and then I get to define a tree. See what I'm saying? So here, a node, each node corresponds to a hyperedge in the graph. That's all I'm saying with this property. Okay, so this is 1-1 property because from now on, if I say hyperedge, that's basically saying, I'm asking you to look at a particular node in this tree, right? So for example, let's try hyperedge CEF. Okay, so you see that's the node there. Okay, all right. So that's 1-1 correspondence, right? Now another, which is very important, it is connectedness. Okay, so connectedness basically says that if you look at any vertex, right? So I'm referring to a vertex in the hypergraph, and look at the subtree. So last time we had a little bit of discussion with this on this concept, right? Subtree. So you look at a vertex and you look at the subtree of T that is induced by this vertex. Oh my God, what does that mean, right? Okay, I hope you still remember. So let's say if we look at you know what, let's give them some names so that I can refer to them. Okay, let's say this is E1, E2, E3, E4, E5. Okay, so if you look at, let's say, vertex E, and then I ask you, what are the nodes uh, containing E? You should tell me, hey, E1, right? And E2, E5. Okay, so that's correct so far. But what's important is, about this connectedness is the following question, right? Do these nodes induce a connected okay, subgraph, all right, of this tree. You see what I'm saying? Okay, so the answer is yes. Okay, you can see that, here, right? So this part is connected, right? Okay. Um, so another question, say C, right? What would be the subgraph or subtree induced by C? That is the subgraph. You see what I mean? As you can see, it's all connected, always connected. Okay, and therefore this connectedness property is satisfied, right? Don't think this is easy. Don't think you can find such a tree for every graph, even if it's cyclic. Okay, so for example, this is a graph that is cyclic. This is just a binary graph, right? Triangle, right? It's cyclic, right? You you find me a tree, and then you don't have to work for the rest of your life. Okay, I will support you. Of course, I won't. I won't do that, right? So it's impossible. All right. Okay, good. So now we have a notion of acyclicity. So this acyclicity is defined through this tree, and this tree is, if exists, right, it's referred to as the John tree. Okay. Well, that's I mean, it's a bit of an anecdote here. Why John tree, right? John, obviously, that's a database thing, right? So why would graph theoretic people? Huh? I don't know why that happens. Should have muted it. Okay. So you see, why would um, something wrong with the computer, huh? Okay, so why would graph theoretic people go with this John tree? John, right? That's a database thing. Well, because this thing, uh, you know, was proposed by database people. As you see, the algorithm that we're going to talk about today, this GYO, yes, that's also an algorithm um, developed in the database. Okay. Anyway, so let's proceed from here. Okay. So today, I'm going to look at a very important fundamental problem, right? So you see, obviously, not every graph, not every hypergraph is acyclic, right? So therefore, here comes a very um, important problem, right? So I give you a graph. How do you know whether this is acyclic? Okay. Um, a graph can be very large. So I mean, if you want to know how we define the graph size, so typically we use V to represent the number of vertices. Okay, but M here, so watch carefully today. Okay, just for today, this is how I'm going to define the graph size. Okay, so you look at basically how many vertices do I need to represent all the edges. Okay, so that's the graph size. All right. So we want an algorithm that runs in time polynomial to n and n, so that we know at least the problem is not NP hard. Right. Okay. As a side product, you will also be able to construct a John tree for a graph that is acyclic. Okay. So you'll be able to do that as a side product. Okay. So the algorithm that we're going to learn is named GYO. Okay, GYO. Okay. In fact, G is one person and YO are another two people. Okay. There are two papers independently developed in this algorithm. It's a GYO algorithm. So that's what we're gonna do today. Okay. All right. So one thing I want you to uh, understand as a super important concept is ear. Okay, ear. So you can think about this ear as another way to say leaf, except that it's not always the leaf. Okay, but uh, think about where ears are on a head. Okay, so you can sort of understand why it's called ear. Okay. Um, After today's seminar, it should be perfectly clear why it's called an ear. Okay. Some edges, let's look at this graph, for example. Some hyper edges are ears, but not all of them are ears. Okay. This ear is a concept defined in the following way. So I will be intentionally verbose. Okay, so if you open a textbook, usually they have a very, very succinct and concise definition for ear, which, in my opinion, is not very, uh, uh, let's say, human friendly in a seminar like this. Okay, so I decided to go a little bit, um, go on a little bit detour. So I will first define what it means by exclusive attribute versus shared attribute. Sorry, bad habit. So I said attribute, right? That's horrible mistake because I didn't define anything about attributes today, right? Vertex, okay? Exclusive vertex or a shared vertex of an edge, of a hyperedge. Okay. Now this is very human friendly, okay? So for example, you look at E4. E4 is here, okay? A is an exclusive attribute. Does that make sense? Does that make sense? You see, I haven't even defined the meaning of exclusive, right? Everybody's getting it, right? So that's what I call human friendly, all right? Okay. All right. So indeed, an attribute, no, vertex. Okay. So this vertex is an exclusive vertex, such as A, right? Exclusive vertex of this hyperedge if no other edge contains this vertex. Okay. So E4 has two exclusive vertices, okay, A and B. All right. So if that's clear, then what will be a shared vertex? So C will be a shared vertex, right? So if this vertex is not an exclusive vertex, and then it's a shared vertex, right? So if you look at E4, right, you can think about like C is the channel that E4 would use to connect to the world. You see what I mean? So that's sort of like the interface, all right, the shear. So this interface is aptly chosen, aptly, okay, aptly, aptly chosen, this word. Why? Because as you will see, um, this shared vertices, and they have a lot to do with this connectedness property. Okay, so this is indeed how this E4 is going to interact with the rest of the tree. Okay, so that notion, that should be clear. Okay, all good? All right, nice. Now ear. Okay, so an edge, oops, a hyperedge. Okay, so I sometimes just say edge um, for convenience. So an edge is an ear, all right, of G, right? So after all, we're talking about hypergraph here, right? If there exists so-called witness, okay, but I'll bring out the name later. Let's say wit. Okay, so this is another edge. Okay, another edge. Okay, so this is something different from E, such that, okay, all, right, so I emphasize all of them, okay, all shared vertices of E, okay, all shared vertices of E are in the witness edge. Okay, so now I can say E wit will be referred to as a witness of E. All right, so basically, E has its property, but this definition requires another edge, so that edge serves as the witness. Okay. So if this definition is difficult, think about the definition you would be reading from a textbook. Okay. All right, now let's play with it. Okay, let's play with it. All right, so think about E4. Think about E4. E4 is an ear. Okay, E4 is an ear. Okay, you know what? There is actually a special case. Okay, I will talk about a patch later on that special case. Okay, so far so good. Okay, so as long as you have two edges in the graph, uh, this definition applies. There's a corner case where you have just one edge. I'll talk about that. Okay, so let's come back to the example I have here. Okay, E4. E4 is an ear. Why? Well, first of all, shared vertices. Okay, you care about shared vertices. Okay, so only C, as I said, right? Good. Then basically the question boils down to, is there another edge containing C, right? The answer is yes, right? E2. And therefore E2 would be a witness of E4 being an ear of the graph. Okay, ear. All right, so next question, how about E2? Is E2 an ear? is E2 an ear? Okay, well, let's again play with the definition, right? So you want to look at sheared vertices. Okay, sheared. What are the sheared vertices in E2? C is sheared, as you can see. E is sheared, and so is F. Okay, all right, so E2 has nothing but sheared vertices. Okay, good. So that should be an ear, right? Because you see C is in E4, E is in E5, and F is also in E5. So, that should be an ear, right? But how come I said it's not an ear? That should be an ear, right? Come on, guys. I said there must be a witness edge containing what? All of the shared vertices, all right? All of them, okay? Of course, every shared vertex will belong to some other edge because that's the definition of shear, okay? All right, but the important thing here is, there must be another witness edge containing all of them. You see what I mean? Blocking your view to the world. Okay, so if that's the case, and then this is an E. Okay, good. All right. So E2 is not an ear. Okay. Next question. How about E5? Is E5 an ear? Is E5 an ear? Yes. Okay, shared vertex. What will be a witness? Witness will be E2, right? Okay, now next, this will be an interesting case. How about E3? Is that an ear? Well, it is. Why? Because E3 has no shared vertices. You see what I mean? So everybody can be a witness. You see what I mean? Okay. You have no shared vertices. Okay, so I trivially can take all your shared vertices, right? So that actually goes correct in logic, right? Okay, so E3 is also an ear. Okay, how about E1? E1 is also an ear. So now you can see an ear is not necessarily a leaf. All right, it's not necessarily a leaf. You can witness here, right? EG is not a leaf. What is the definition of leaf? You have only degree 1, and then it's a leaf, right? But EG has 2 edges, right? Okay, good. So today, a very big part of our seminar will be devoted to learning about ears. Okay, we'll see this is standing at the very center of this notion of acyclicity. Okay. All right, so let me first give you the good stuff, uh, and then I'll talk about the bad stuff. Okay, so the good stuff will be the algorithm. Okay, the bad stuff will be theory. Okay, good stuff, tasty stuff is usually not very nutritious. Okay, it's the bad stuff that gives you the nutrition. You see what I'm saying? All right, but anyway, I know most students come here for the good stuff. Okay, and maybe not you guys. Okay, in a standard presentation, people want me to talk about algorithms and no theory. Okay, so yeah, sure, I go with that. So algorithm. Okay, so let's talk about the GYO algorithm. So this GYO algorithm says the following. You give me a graph. Okay. All right. So I'm going to tell you whether this is a cyclic. Well, for convenience, let's make a copy of it. So this is ordinary VE. Okay. So this is a copy of the beautiful VE. Okay. All right. Good. Now GYO says, okay, do you have an ear? Does the current graph has an ear? Okay, if it does not, terminate. Okay, terminate and do something. I'll tell you later. Okay, make a decision. Make an easy decision. But if it still has an ear, you want to pick the ear. Actually, you could have multiple ears, as you can see, right? Okay. Um, Pick an arbitrary ear. Any ear. Actually, any. I don't like the word any because it could be ambiguous, right? An arbitrary ear of the graph so far. Okay? This is the ordinary graph, all right? The ordinary VE, okay? All right, and take the exclusive attribute. So let's say U, sort of like unique, right? Exclusive. So this is the set of exclusive attributes, not attributes, sorry, vertices in the ear. That's fair, right? Because every edge, I mean, this exclusive vertex concept applies to any edge, right? So it applies to an ear as well. And then I'm going to remove the edge from the graph. Remove it. But the thing is, if you remove the edge, some vertices will also have to be gone, right? What are those vertices? I mean, if it's a shear vertex, I mean, this vertex still appears somewhere else, right? Okay, so if it's an exclusive vertex, if it's a vertex exclusive to E, and then this vertex will have to be gone, correct? Okay, so we update the graph in the following way. So for the edge set, that's easy. Okay, so you want to remove the ear. Basically remove the edge in English, right? But mathematically do a set minus, right? And then accordingly, you want to remove the unique vertices. Okay, you want to remove the unique vertices of the U. Okay. So now you lose one edge. You see what I mean? So every iteration will lose one edge. Okay, so the number of iterations will be bounded by this number of edges. Okay. So you keep doing. Oh, before I go on, I want you to get convinced that at all times, this E, you think about it, right? E, for this VE to make sense, to serve as a hypergraph definition, you gotta be careful, right? Every element of E, which means every hyperedge of E, right? We'll have to use only the vertices currently in V, correct? All right. But you gotta be careful because I removed some vertices, right? U, right? Those vertices in U are removed, so you gotta be able to convince yourself that that's okay. It's not going to violate our hypergraph definition, right? But I think this should be quite easy to verify because of the exclusivity. Right? Very nice. Good. So now you keep going. And let's see if you are able to remove all the edges. Okay. So when you terminate, there are two possibilities. Is what I'm saying. You remove all the edges, so it's an empty graph. If this E, the set of edges is empty, and then so is V. You see what I mean? V will have to be empty as well. So basically, you end up with empty-empty. V is empty and E is empty, right? But there's another possibility. So what I mean, there's another possibility. Okay, at some point, you can find no more years, and then you have to finish as well, right? So depending on whether the graph is empty, you make a decision. So if V is empty, and then say a return acyclic, else return cyclic. That's the algorithm. That's the algorithm. Okay. All right. We seem to have some doubts about this. Okay, that's good. So let's run it. Let's play with the algorithm. Let's say we start with this. Okay. So um, you want to find an ear. Okay. So you have four choices here. Okay. It doesn't really matter which one you pick. Okay. So how about we pick E1? It's just for fun. All right. So we pick E1. And then the algorithm will say, okay, I'm going to remove E1. Okay, so G will also get removed, but that should be clear, okay? All right. So now the graph has four edges left, okay? You want to see if you have another ear. Do you have another ear? Well, at least we have E3, right? How about CEF? Is CEF an ear of the current graph? Current. the current graph has 4 hyperedges only, okay? CEF is not an ear, right? So you have 3 choices, E4, E5, E3 are still ears. Which one would you like to go next? How about E5? Okay, all right, so now you have 3 edges left. Okay, so I think this starts to be boring, right? So next you could remove E3 or E4, that's a E3, and then next E4. And now CEF is an ear. This reminds me, I forgot the patch that I promised you, right? Okay, so let's go back to the definition of ear. So here I assume that you have at least 2 edges, okay, so that you can find witness, right? But that's too demanding, right? If you have only 1 edge, right? How can I give you another edge? You see what I mean? So if the whole graph has only 1 edge, and then this edge itself is an ear, period. Okay, so now CEF is an ear. Is that all right? CEF. Actually, you know what? CEF already became an ear at this point. Okay, let's got E3 removed, right? So here CEF is already an ear. Okay. But anyway, let's say you remove ABC. When you have only 1 edge left, this is definitely. Yes.
I have a minor question. If there is an attribute in the hypergraph that is not connected by any hyperedge, then the graph is.
Wait. Slow down. So a vertex? Okay, I see. Yeah, sure. Okay, so in that case, you are right. So you could have, for example, ABC, but the edge set is empty, right?
Yeah.
Okay, sure. Okay. All right. So this basically says my definition of a hypergraph is not very rigorous. Okay. So I should define a hypergraph with a V as always the union of the all the hyperedges.
Okay.
That will make it rigorous in the context you just asked me about. Okay, all right. So let's stay with that definition. So that's basically the reason why we will have to remove the exclusive set, right? Otherwise, we could just leave U there. But yes, it's a good point. Or I could say, if this Y is empty, and that would be another way to answer your question. But as you said, that's a minor. All right. So on the other hand, if you have a cyclic graph, let's say if you go with AB, BC, and CA, and then you can find no ears. You can find no ears. Okay, there are no ears here. Okay, so the algorithm is going to terminate. Good. So before we proceed to theory, let's first convince ourselves that this is polynomial time doable. Okay, so first of all, the number of iterations is clearly bounded by the number of edges, right? The number of edges is bounded by m trivially. Okay, so that will be fine. When I say polynomial, I mean polynomial in n and in m. Okay, all right. So if you look at 1 iteration, you can see basically you have to find an ear, right? Find an ear. So if you think about it, an ear basically says, okay, I first determine whether, for every edge, right? You can do each edge one by one, right? You look at this edge, you look at each vertex in the edge, you ask the question, is this exclusive or shared, right? But this is something you can check polynomial time. And if it's a shear, then you collect all the shear vertices and you want to check whether they are contained by another edge, right? So everything is easily polynomial time doable. So this is a polynomial time algorithm. Cool. All right, now let's start the second part of the seminar. We have 20 minutes left, and let's hope that will be enough. Quite uncertain about that. So we're going to talk about ears, okay? And we will learn some nice properties about ears. So let's say this is the first property, okay? So here we've got a graph. So let's say this E is an ear of G. Okay. Well, I told you before that you might be able to find me a tree, a joint tree. By the way, I forgot to say this is acyclic. Okay, G is acyclic. Okay. So I forgot to say, yeah, the G is acyclic, something I forgot to say. So earlier I said you are able to find me a joint tree of G where this ear may not be a leaf, right? You witnessed an example before, right? Okay. On the other hand, the following is true. Okay, so there must exist a joint tree T of G in which E is a leaf. Okay. Now let's go back to this example here. Okay. So as you can see, this example, in this example, if you look at ear E1, so if you look at ear E1, this is not a leaf, right? So what if I say you have to find me another joint tree? And in this joint tree, E1 is a leaf. Are you able to do that? Are you able to do that? Okay. So let me show you how to do this. Okay. Let me show you, because this is also a procedure that we're going to utilize in the proof. Okay. Now, watch carefully. Okay. So this EG is an ear. I'll find a witness. Actually, I'll find a witness from one of its neighbors. Okay. I'll see CEF. That's a witness, right? So what I'm going to do is I will break this edge, break it. So if I break this edge, and then this tree becomes disconnected, you see what I mean? Okay, now I have to somehow be able to connect it back, connect different components back, right? So if you think about it, EG, I will look at the other neighbors of EG, right? I'll try to get those neighbors connected back into the tree, right? Now, in this case, EG has only one neighbor. Okay, so that's H. All right, so what I'm going to do is I will, did I say I will break this edge? I will not break that. Okay, I will not break that. Okay, I'm so sorry. I don't break it. All right, so no disconnection. Okay, so what I'm saying is you look at every other neighbor. That part is still valid. Okay, so you look at this H, right? You break that edge. Okay, now this part becomes disconnected. But what you want to do instead is to connect this H to its the witness of this ear. That's what you do. Okay. So after you do this, and then if you look at this ear, right, it has no edges but one, because I didn't break. I corrected myself, right? I didn't break the edge between itself and the witness. So this becomes a leaf. Okay. Now let's look at the resulting tree, right? So as a human being, you can see in this particular example, we have got another joint tree. It is indeed a joint tree because you see 1, 1, no problem. Connectedness, do you have connectedness? Well, for this example, you can verify as a human being that indeed you have connectedness. Okay, later we will prove you always have connectedness. Okay, that's not super difficult, but there is some logic behind it. So this is the joint tree. Okay. So anyway, this is what the lemma says. Okay, this is what the lemma says. You can always find me a joint tree in which this V is. Okay. So I will not prove the lemma now. I won't prove it now. Okay, because if I prove it now, it's going to make it less interesting for you. Okay. You know, oftentimes a problem is, seems difficult. For example, now the problem is I want you to prove the correctness of GIO, right? So that seems difficult. But then the thing is, after you have already learned about the key lemmas, and then this will become much, much easier. All right, so it's a matter of whether you know the key lemma. Now, this is a key lemma. So I'll use this lemma. I will continue to explain to you how come GYO is correct. So this is the first lemma we'll need. Okay. Well, there was a very important corollary of the lemma. Okay, that's a corollary 2. Okay. If you remove an edge from an acyclic graph, you preserve acyclicity. Okay. Well, think about, I mean, this is obviously true for conventional binary graphs, right? If you have an acyclic graph, and then you have either a tree or a forest, that's what I mean. And then if you remove an edge, then you will have more trees in the forest. Okay, so of course it's acyclic. However, for hypergraphs, where this acyclicity notion is more complex, it's you can no longer prove this seemingly innocent statement in the same way. Is what I'm saying. Okay. So now if I say proof, right? If G is acyclic, it remains acyclic after removing an edge. How do you do it? Okay, after removing, okay, you know what? I'll make it easier for you here after removing an ear. Okay, so this is going to make it a little bit easier. Okay, because this will be a corollary. A corollary. Okay, so before that was also true, but that's not a corollary. So we only need this corollary. All right, so I can talk about this corollary here because this is to, yeah, it's okay. This is to apply lemma 1. Okay, are you able to prove this? I mean, if any one of you can see how to prove this, that would be awesome. All right, so the idea is this, right? So by lemma 1, right? So let's say if you have this ear E, right? So you can find a tree. Let's say this is a tree, okay? And for this tree, this E is a leaf, okay? So this is from lemma 1. See what I mean? Okay, right? So now you think about the graph without this E, right? Yeah, so all you have to show is that you can find a John tree. That's what I'm saying. Okay, so that is a John tree. So 1-1 correspondence, obvious. That's obvious. And if you look at connectedness, right? So you look at all the remaining attributes, right? So you see basically the subgraph induced by the nodes containing that attributes remain the same, except for maybe E has gone, right? So this is why this is correct. Okay, good. All right. Now, there's another lemma, but this lemma is much easier. Okay. So this says the following. If G is acyclic, okay, or another way to say the same thing is if G has a John tree, and then every leaf of T is an ear. Okay. Well, if you think about lemma 1 and lemma 2, they sound similar. Okay. Except that in lemma 1, yeah, we're saying there exists a John tree. So I mean, okay. So that's really from the POV point of what's that? Point of view, yes. Point of view, POV of ear, right? Now here from lemma 2, it's like from the POV of a John tree. So I mean, okay, good. So that corresponds, that establishes some correspondence between the notion of leaf and ear. Okay, so that's why sometimes you hear people say, "Oh, an ear, that's a leaf." Okay, so this derivation is not completely it's not complete at least, right? So jumping some steps in between, but now you understand why. Okay. All right, so this lemma is quite easy to prove. Okay, so I will present a sketch here. Okay, so let's say this is a tree, right? So you look at a leaf, right? Okay, so you want to prove that this yi is an ear. Okay, well, if this is the case, and then you know you will have to be concerned with the shared attributes of this yi, right? And you want to argue that there's some other guy in the tree containing all the shared attributes of yi. Okay, but this is quite easy, right? Because due to connectedness, right, just have to look at its neighbor. And there's only one neighbor because yi is a leaf, right? So I argue that every shared attribute of yi will have to be covered by yi prime. Okay, that's due to connectedness. You see what I'm saying? Because you know this all the nodes containing this any attribute will have to be connected. All right. So if an attribute is in yi and it's not in yi prime, you're creating a gap here. And then in somebody else, and then then you will see that hey, those guys cannot really. I mean, these nodes cannot really get connected. You see what I'm saying? That would be a hole there, right? So this is why this yi prime can serve as a witness. Okay, good. So these three are the three fundamental results I want you to know about ears. Okay, and then with this we can prove the correctness of GYO. Okay. All right. Next, let's prove the correctness. You owe you the proof of lemma 1. I will leave that to the end, maybe after the seminar. So the next one is, okay, if, V is empty. So V is empty, this means at the end of GYO. Okay, so I will write a few more words here. At the end of GYO. Okay, so you see that's the only condition for GYO to claim acyclicity. So I mean, okay. So this means G is acyclic. So this is one direction, right? There's another direction saying G is acyclic. And then you definitely have that GYO. I mean, definitely this V will be empty at the end of GYO. All right, so let's prove lemma 5 first. By the way, this is proving if and only if, as you can see. Okay, good. Now, let's prove lemma 5 first, because lemma 5 is fun to prove. Okay. So think about the following argument, right? You see, since G is acyclic, right? And then G has a joint tree, and therefore it definitely has at least 2 ears, right? Anyway, we need only one, right? So you cannot say that G has no ears, you see what I mean? And therefore, GYO will have to be the GYO will have to go into one iteration. So I mean, because it cannot say, all right, I didn't find any ears, because there are ears there. Good. So what a GYO does is to remove this ear, an arbitrary ear, of course, right? But we prove in corollary number 2 that if you remove an ear from the hypergraph, acyclicity is preserved. You see what I'm saying? Good. And therefore, now if you go into the beginning of the second iteration of GYO, GYO must be still looking at an acyclic graph. You see what I'm saying? All right. And then for that acyclic graph, there must be another ear. Yeah. So GYO will have to perform a second iteration. So I mean, we'll have to remove another edge. But then this argument is going to work by itself now, right? So GYO will be forced to keep removing edges, right? One at a time, right? But in the end, you have only a finite number of edges, right? In the end, all of them will get removed, right? So lemma 5 is established in this way. Okay, nice. Okay. Now let's prove lemma 4. Okay, so I'll get lemma 5 out of the way. All right, so now let's prove lemma 4. Okay, so let's prove it. All right. So now we know that the algorithm has been able to complete all the edge removals, right? You can see that the algorithm removes one edge at a time, right? So basically, it transforms the original graph into many other graphs one step at a time, right? So let's just say that V0, E0, so that is the original graph. Okay. So after removing one edge, we get V1, E1. Is that all right? After removing another edge, we get E2, E2, and so on and so forth. So some T. Okay. So T is basically the number of edges in the original hypergraph. Okay. So we go down this sequence here, correct? Okay. By the way, what can you say about this VTET? Well, this VTET is definitely phi, because that's the if condition here, right? Because here we say, okay, everything, I mean, the algorithm has run all the way to the end, everything's empty. Now you want to argue that the original graph is a cycle. So that's the deal here. Okay, good. Very nice. Okay. So I want you to prove V0, E0 is a cycler. Okay. So we will apply an inductive argument, inductive. We're going to go backward. That's what I mean. We're going to go backward. Okay, so you can see the last one is trivially acyclic. Okay, and then I want you to prove that if VTET is acyclic, and then the previous one, T minus 1, E minus 1, that must be acyclic as well. And in turn, I want you to argue that still the next one, the previous one, T minus 2, E minus 2, okay, VT minus 2, E minus 2, will also have to be acyclic. And then all the way back to V0, E0. See what I mean? Okay, good. And therefore, now the core of the argument is basically this: know that VI EI is acyclic. So I want you to prove that VI minus 1, EI minus 1 is also acyclic. Okay, so this is what I want you to prove. Right. Okay, good. All right, so now let's see. Think about the execution of GYO, right? So the execution goes like this, right? So you have this as the input for that iteration. You see what I'm saying? Okay. And then an edge, this is an ear of this this I minus 1 hypergraph. Okay. So you want to remove that, and then you get this VI, EI, right? So that's how it runs. That's what I mean. Okay, good. All right. Okay, good. So now, as you can see, Yi is an ear. So if Yi is an ear, and then there are two possibilities. Okay, the first possibility is that this VI minus 1 contains just a single edge. Contains just a single edge, right? Okay. And then another possibility is that this ear has a witness. Okay, so there are two possibilities. So in the first possibility, if this EI minus 1 has just a single edge, by the way, that means this EI is empty, right? Because it gets removed. Anyway, it has only a single edge, and then it's trivially acyclic. Okay, so therefore this case is easy. Okay, it's not so interesting. Okay, good. All right.
So why do we need the first case? I think even if there is induction, basically, E is the only edge. E minus 1.
Can I try to answer it?
Okay.
Okay. So yeah. Anyway, I want to answer that anyway because it helps. This is because next I want to use a witness. But the thing is, I will not be able to say you have a witness if there's only one edge in the graph, right? So that's why yeah. Okay, so now let's consider the case where Y has a witness. All right, so let's say Y wit is a witness of Y in Vi minus 1, Vi minus 1. Okay, good. Now I have earned the right to say this, right? Okay, good. So now I'm going to argue that I can find a John tree for this I minus 1 graph, right? Now remember, the direction is backward, okay? So you already know that the I graph is acyclic. You want to argue that I minus 1, E minus 1 is also acyclic, right? So this is what I'm going to do. So I would say, okay, find me a John tree for VI. All right, so find me there. Well, you have to give it to me, right? You cannot deny my request. Why? If you deny my request, you're a bad guy because you must be lying, right? Because you told me in my face VI is acyclic, right? If it's acyclic, it has a John tree. You have to give it to me. Okay, you cannot hide it. All right, good. So now, okay. So this is the, okay. So this is the tree. I don't really care, but I want to show it like this for a reason that will be clear later. Good. So that's the tree. And then I'm going to ask you, okay, where is Yi wit? Give me Yi wit in the tree. All right. Well, the tree has 1-1 correspondence. You see what I'm saying? You cannot say Yi wit is not here. Yi wit must be here somewhere. All right. But of course, it may not be a leaf. I cannot say, give me a tree where Yi wit is a leaf. That will be too much. Right. But that's not what I'm asking. Okay, you have to give it to me. Let's say it's here. So this is Yi wit. Okay. All right. Good. That's all I need. So what I'm going to do is I will create another child, not child, sorry, my mistake. Not child, because this is not a rooted tree, right? Okay, so I'll create another edge, all right? So this edge is between Yi and Yi wit. And then I'll prove now this tree is going to be a John tree of this Vi minus 1, Yi minus 1. Okay. All right, so good. So many of you can see this already, right? Why? Well, think about the shared attributes of E, correct? I know that all those shared attributes will have to be inside E wit. Is what I mean? Okay, because that's the definition, right? And therefore, this E wit, helps E to ensure this connectedness properly. Actually, that's not a correct thing to say helps Yi. But what I'm trying to say is make sure that for every such attribute, right? So if you look at the subgraph induced by this attribute, I mean, now compared to before, now there's one more node, which is Yi, right? But Yi with the stick. And therefore, it gets everything connected still. Okay. All right. So as you can see, not too difficult, right? Not too difficult. I mean, this correctness of GYO is not supposed to be easy, but now, as you can see, it's not too difficult, right? Why isn't it difficult? Because, once again, you already know the key lemmas, okay? In fact, I have proved all of these things except one, okay? So let's get everything removed. Let's get everything removed because we don't need that anymore. And the only thing left is to prove lemma 1. By the way, this is the end of the seminar, okay? So you can leave if you want. Okay. All right. So now this lemma 1 is actually the most difficult one. Okay. This lemma 1 will require maybe another 20 minutes to this. So this lemma 1 here, it says, you look at an ear. Basically, you have to find me a tree. Okay, you have to find me a tree. And Yi is a leaf in the tree. Okay, how can you do that? Right. So you saw an illustration before. We did that for Yi1. Okay, we did that for Yi1. But you have to argue in general that this is always possible. Okay, how can you do that? So with this, and then your understanding about ear, I would say is going to be deeper, because now you will get really convinced why this is called an ear. You see what I'm saying? So this is basically the reason why it's called an ear. Okay, so essentially it's a leaf. If you look at the head somehow, you see what I mean, from the right angle, that it's an ear. Okay. All right. So how do we do this? Okay, let's see how we do this. Okay, so let's prove it. All right. So the basic idea is very easy. So you want to start with an arbitrary geometry. That's not too surprising. Okay. You want to start an arbitrary geometry, and then we're going to convert that geometry into another one that we really need, right? So that's the argument, right? Okay. So you want to go with this direction. Okay, so you say, okay, take a geometry of G. All right, so let's say this is T star. Okay, so this is sort of like the anchor geometry that we will modify. Okay, so we'll convert this into a geometry satisfying our requirement. So if Y is already a leaf of T star, we're done. We say thank you very much, and then we're done. Okay. All right. So of course it's not that lucky, right? So now I'm going to prove a claim, right? I'm going to prove a claim. I would have to find myself a good witness. Okay. So for example, let's say E4. Of course, E4 is a leaf, but the point I'm trying to make is for E4, everybody else can serve as a witness, right? Okay. In order to continue my argument, that would not be enough. Okay. By the way, E4 could be somewhere in the middle, right? E4 could be our ear in the argument, right? So in order to continue the argument, I have to find a good witness. But fortunately, we are always able to find a good witness. And this witness is extremely close, thanks to connectedness. Okay, we can always find a very, very friendly witness that's going to do us a lot of help later. And this witness will always be a neighbor of this ear. Okay, so this is the first claim. Okay, one neighbor of E must be a witness of E. Okay, all right. So let's prove it. Okay, so this is not too difficult to prove once you know what to prove. Okay, so first of all, let's think about the shared vertices of E. Okay, you could say none. You could say none. But if you say none, I would say thank you very much. Why? So you say none. I know everybody can be my witness, right? So this means every neighbor can be my witness, right? So I would have said all neighbors of Yi are my witnesses, right? So I say thank you very much in that case, right? Okay, so now you say, okay, you change your mind. Let's say X is let's say the Yi has at least one shared vertex. Okay, so X is an arbitrary shared vertex of E. Okay, good. Well, but I gotta be careful. I cannot say, okay, now give me the neighbor that contains X. All right, that would be too much because you could still deny me. You could say, why? Why do you think there is such a neighbor? Right. So I cannot really go, in terms of the logic, I cannot go like this. Right. But the thing is, I go with shear. Hey, what's the definition of shear, man? When you say shear, right, it means this X is not only in E, correct? Because by definition, right, it's also in another edge, right? So let's say, so I have the right to say, okay, so this is another edge containing X. Now this is my right. You see what I mean? You cannot say, I don't have E prime for you, right? If you don't have E prime for me, then you must be lying just now, right? Why did you say X is a shared vertex? You see what I mean? So this is my right. Okay, good. Now, and then I can ask you, okay, since this is the case, and then where is E prime in the tree? One-way correspondence, okay? You cannot say E prime is not in the tree, okay? So E prime is there. E is there and E prime is there, all right? Good. And then I consider the simple path in the tree from E to E prime, all right? You see, every step is very powerful. I make my argument only within my scope, right? So it's like all these blows are very effective for one blow at a time until you pass out. You see what I'm saying? That's the argument. Okay, you cannot deny anything I request, right? So I say, okay, find me this path, this simple path connecting Y and Y prime. This is a tree. Okay, you have to remember it's a tree. It's not even a forest. Okay, it's a tree, right? So I take any two nodes in the tree. There is one unique path. You see what I mean? I say, find me that path. All right. Okay, my right. Okay, so you have to give me that path. Okay, very good. Now I'm gonna proceed like this. X is in Y. X is in Y prime by the connectedness property. Connectedness. X will have to be on all the nodes, in all the nodes on this path. Okay. Otherwise, X will break your connectedness property. So I mean, okay, you remove this node and then the nodes get disconnected. You see what I'm saying? Okay. And therefore, X appears in all the nodes on the path. Good. Now I can say, give me that neighbor. You know what I mean? So this guy, I mean, on this path, right? There must be a neighbor. There's only one guy on this path adjacent to E. You see what I mean? And therefore, that guy is the one I'm looking for. That's a sound, right? You can see this is really a powerful argument because you don't get to say no to every request I make, right? Okay. Good. All right, nice. So that's claim number one. Okay, I definitely have a neighbor that can help me. Okay, good. So that's claim number one. So now we have it. Okay. Very nice. So the rest is not too difficult now. So this is a E witness. Okay. And then I'm going to start modifying the tree. All right. So from T star, I'm gonna go like this. So I'm going to describe the procedure pictorial. Okay, so this is Yi, and this is Yi witness. You see what I mean? Okay, fair enough, right? And the Yi has some other, has at least one other, this Yi has at least one other edge, right? Otherwise, Yi would be a leaf, and then we'll be done, right? Okay, so let's say that these are the edges of Yi. Okay, I don't really care how many it has, but just for illustration, let's say it has three other neighbors. Is that all right? Okay. So now you can see here there is some subgraph, and here this is some subgraph. Fair enough, right? Okay. And by the way, on this side, there's also some subgraph. Is that all right? Okay. So you look at these three neighbors. Okay. All right. So what I'm going to do is I'll break this edge. I'll break these three edges. I'll break these three edges. And then I create three new edges. Okay, good. Now verify a few things. First of all, let's look at the new modified graph, okay, from T star. Is this a tree? Is this a tree? It is a tree. If it's not a tree, tell me, how can you have a cycle? See what I mean? Okay, all right. So I'm not going to go into this, but I trust you can argue. You can provide a powerful argument, just like the one I gave. One punch at a time, right? So one punch at a time until you pass out, right? So that's the idea, right? So yeah, you have to find me such an argument to prove that this is indeed a tree. Okay, so that's one. Second, is Yi a leaf in this tree? Well, of course. I just look at how many edges this Yi still has, right? I removed all but one, right? So the only edge that has not been removed is the one from Yi, between Yi and its witness, correct? Okay, good. All right. But we're not done yet, right? We still have to prove that this tree, let's call it T, is a joint tree, right? Okay, so two properties, right? The first property is, okay, how about 1, 1? 1, 1, that's trivial, right? Okay, good. Now, how about connectedness? Okay, now we have to talk about connectedness. Okay, good. All right, so not too difficult. This is actually fun. So let's talk about this attribute X. Okay, so we have to prove that for every attribute X, the nodes containing X are connected. Okay. All right, so we will talk about three categories. Okay, the first category is that X is not in E. X is not in E. You see what I'm saying? Okay. Okay. So if X is not in E, right? And then if X is not in E, now let's think about in the original tree, right? The blue part. Okay, where can be the subgraph of X be? You see what I mean? All right. So convince yourself it can be entirely here. Okay. By the way, it cannot include this E, right? You see what I mean? It cannot include this E, so it can be entirely here, or it could be entirely here, or entirely here or here. You see what I'm saying? Right? Because it cannot contain E, right? You cannot say like, oh, I contain some guy here, and then you're in trouble, right? Because to get these two parts connected, you have to go through E. You see what I mean? But E does not contain. Now, this is the first category, right? X is not in E. That's what I said, right? So X is not in E, and therefore the subgraph of X will have to be entirely here, or here, or here, or there. You see what I mean? Okay, good. But our changes are not going to affect those subgraphs. You see what I mean? All right. So therefore, those subgraphs, I mean, that the subgraph of X must still be connected after the changes, right? So this is fun, right? Now another possibility is that this is exclusive to E, right? Now this is easy, exclusive, right? What is the subgraph of this X? Oh, it's just here, just one guy. Okay, then this is trivial, correct? Okay, good. Now let's think about the remaining case, right? This is shared vertex of E, right? Now let's think about the difference, right? The difference before and after, right? You see, so this X definitely in E mid, right? Definitely in E mid. Okay, so now I'm going to ask the question: is X in this neighbor? Okay, so if this X is not in this neighbor, and then this part cannot be in the subgraph induced by X. You see what I mean? Because I know that the subgraph before, right, will have to include E, and also will have to include E width as well. Okay, you see what I'm saying? All right, good. So if you contain something here and here, I mean E width, right, and then you have to go through then you have to go through the neighbor, right? So this is impossible, correct? Okay, good. Now, on the other hand, if this neighbor contains this X, okay, and then it could extend all the way into this subgraph, right? The subgraph of X, right? So before it was connected through this edge here, right? And also to E width, you see what I mean? And now what will be the new subgraph? The new subgraph goes through the green edge and then back to E here. So everything's still connected, right? Okay, so this is the argument, right? So as I said, this is fun, right? Okay, good. So this concludes today's seminar. Okay, thank you very much for listening. I hope this makes sense to you. Okay, so now you understand the importance of ears. Okay, all right. So this is all for today. Bye.